A steam turbine is a device which extracts thermal energy from pressurized steam and uses it to do mechanical work on a rotating output shaft. Its modern manifestation was invented by Sir Charles Parsons in 1884. Because the turbine generates rotary motion, it is particularly suited to be used to drive an electrical generator. About 90% of all electricity generation in the United States is by use of steam turbines. The steam turbine is a form of heat engine that derives much of its improvement in thermodynamic efficiency from the use of multiple stages in the expansion of the steam, which results in a closer approach to the ideal reversible expansion process. History. The first device that may be classified as a reaction steam turbine was little more than a toy, the classic Aeoli pile, described in the 1st century by Greek mathematician Hero of Alexandria in Roman Egypt. In 1551, Taqi al-Din in Ottoman Egypt described a steam turbine with the practical application of rotating a spit. Steam turbines were also described by the Italian Giovanni Branca and John Wilkins in England. The devices described by Taqi al-Din and Wilkins are today known as steam jacks. The modern steam turbine was invented in 1884 by Sir Charles Parsons, whose first model was connected to a dynamo that generated 7.5 kilowatts of electricity. The invention of Parsons' steam turbine made cheap and plentiful electricity possible and revolutionized marine transport and naval warfare. Parsons' design was a reaction type. His patent was licensed and the turbine scaled up shortly after by an American, George Westinghouse. The Parsons turbine also turned out to be easy to scale up. Parsons had the satisfaction of seeing his invention adopted for all major world power stations, and the size of generators had increased from his first 7.5 kilowatts setup to units of 50,000 kilowatts capacity. Within Parsons' lifetime, the generating capacity of a unit was scaled up by about 10,000 times, and the total output from turbo generators constructed by his firm C.A. Parsons and Company and by their licensees, for land purposes alone, had exceeded 30 million horsepower. A number of other variations of turbines have been developed that work effectively with steam. The Laval Turbine accelerated the steam to full speed before running it against a turbine blade. De Laval's impulse turbine is simpler, less expensive and does not need to be pressure-proof. It can operate with any pressure of steam, but is considerably less efficient. Fr. Auguste Rateau developed a pressure-compounded impulse turbine using the de Laval principle as early as 1896, obtained a U.S. patent in 1903, and applied the turbine to a French torpedo boat in 1904. He taught at the École des Mines de Saint-Étienne for a decade until 1897, and later founded a successful company that was incorporated into the Alstom firm after his death. One of the founders of the modern theory of steam and gas turbines was Aurel Stardala, a Slovak physicist and engineer and professor at the Swiss Polytechnical Institute in Zurich. His work Die Dampfturbine und ihre Aussichten als Warmkraftmaschinen was published in Berlin in 1903. A further book, Dampffund Gas Turbine, was published in 1922. The Brown-Curtis turbine, an impulse type, which had been originally developed and patented by the U.S. company International Curtis Marine Turbine Company, was developed in the 1900s in conjunction with John Brown and Company. It was used in John Brown-engined merchant ships and warships, including liners and Royal Navy warships. Manufacturing. The manufacturing industry for steam turbines is dominated by Chinese power equipment makers, Harbin Electric, Shanghai Electric, and Dongfang Electric. The top three power equipment makers in China collectively hold a majority stake in the worldwide market share for steam turbines in 2009-10, according to Platts. Other manufacturers with minor market share include BHEL, Siemens, Alstom, GE, Mitsubishi Heavy Industries, and Toshiba. The consulting firm Frost & Sullivan projects that manufacturing of steam turbines will become more consolidated by 2020 as Chinese power manufacturers win increasing business outside of China. Types. Steam turbines are made in a variety of sizes ranging from small less than 0.75 kilowatts units used as mechanical drives for pumps, compressors and other shaft-driven equipment, to 1,500,000 kilowatts turbines used to generate electricity. There are several classifications for modern steam turbines. Blade and stage design. Turbine blades are of two basic types, blades and nozzles. Blades move entirely due to the impact of steam on them and the profiles do not converge. This results in a steam velocity drop and essentially no pressure drop as steam moves through the blades. A turbine composed of blades alternating with fixed nozzles is called an impulse turbine, Curtis turbine, Rotor turbine, or Brown-Curtis turbine. Nozzles appear similar to blades, but their profiles converge near the exit. This results in a steam pressure drop and velocity increase as steam moves through the nozzles. Nozzles move due to both the impact of steam on them and the reaction due to the high-velocity steam at the exit. A turbine composed of moving nozzles alternating with fixed nozzles is called a reaction turbine or Parsons turbine. Except for low-power applications, turbine blades are arranged in multiple stages in series, called compounding, which greatly improves efficiency at low speeds. A reaction stage is a row of fixed nozzles followed by a row of moving nozzles. Multiple reaction stages divide the pressure drop between the steam inlet and exhaust into numerous small drops, resulting in a pressure-compounded turbine. Impulse stages may be either pressure-compounded, velocity-compounded, or pressure-velocity compounded. A pressure-compounded impulse stage is a row of fixed nozzles followed by a row of moving blades, with multiple stages for compounding. This is also known as a Rotor turbine, after its inventor. A velocity-compounded impulse stage is a row of fixed nozzles followed by two or more rows of moving blades alternating with rows of fixed blades. This divides the velocity drop across the stage into several smaller drops. A series of velocity-compounded impulse stages is called a pressure-velocity compounded turbine. By 1905, when steam turbines were coming into use on fast ships and in land-based power applications, this was more efficient with high-pressure steam due to reduced leakage between the turbine rotor and the casing. This is illustrated in the drawing of the German 1905 AEG marine steam turbine. The steam from the boilers enters from the right at high pressure through a throttle, controlled manually by an operator. It passes through 5 Curtis wheels and numerous reaction stages before exiting at low pressure, almost certainly to a condenser. The condenser provides a vacuum that maximizes the energy extracted from the steam, and condenses the steam into feed water to be returned to the boilers. On the left are several additional reaction stages that rotate the turbine in reverse for a stern operation, with steam admitted by a separate throttle. Since ships are rarely operated in reverse, efficiency is not a priority in stern turbines, so only a few stages are used to save cost. Blade design challenges. A major challenge facing turbine design is reducing the creep experienced by the blades. Because of the high temperatures and high stresses of operation, steam turbine materials become damaged through these mechanisms. As temperatures are increased in an effort to improve turbine efficiency, creep becomes more significant. To limit creep, thermal coatings and superalloys with solid solution strengthening and grain boundary strengthening are used in blade designs. Protective coatings are used to reduce the thermal damage and to limit oxidation. These coatings are often stabilized zirconium dioxide-based ceramics. Using a thermal protective coating limits the temperature exposure of the nickel superalloy. This reduces the creep mechanisms experienced in the blade. Oxidation coatings limit efficiency losses caused by a buildup on the outside of the blades, which is especially important in the high-temperature environment. The nickel-based blades are alloyed with aluminum and titanium to improve strength and creep resistance. The microstructure of these alloys is composed of different regions of composition. A uniform dispersion of the gamma prime phase, a combination of nickel, aluminum, and titanium, promotes the strength and creep resistance of the blade due to the microstructure. Refractory elements such as rhenium and ruthenium can be added to the alloy to improve creep strength. The addition of these elements reduces the diffusion of the gamma prime phase, thus preserving the fatigue resistance, strength, and creep resistance. Steam supply and exhaust conditions. These types include condensing, non-condensing, reheat, extraction and induction. Condensing turbines are most commonly found in electrical power plants. These turbines receive steam from a boiler and exhaust it to a condenser. The exhausted steam is at a pressure well below atmospheric, and is in a partially condensed state, typically of a quality near 90%. Non-condensing or back pressure turbines are most widely used for process steam applications. The exhaust pressure is controlled by a regulating valve to suit the needs of the process steam pressure. These are commonly found at refineries, district heating units, pulp and paper plants, and desalination facilities where large amounts of low-pressure process steam are needed. Reheat turbines are also used almost exclusively in electrical power plants. In a reheat turbine, steam flow exits from a high-pressure section of the turbine and is returned to the boiler where additional superheat is added. The steam then goes back into an intermediate pressure section of the turbine and continues its expansion. Using reheat in a cycle increases the work output from the turbine, and also the expansion reaches conclusion before the steam condenses, thereby minimizing the erosion of the blades in last rows. In most of the cases, maximum number of reheats employed in a cycle is 2, as the cost of superheating the steam negates the increase in the work output from turbine. Extracting type turbines are common in all applications. In an extracting type turbine, steam is released from various stages of the turbine, and used for industrial process needs or sent to boiler feed water heaters to improve overall cycle efficiency. Extraction flows may be controlled with a valve, or left uncontrolled. Induction turbines introduce low-pressure steam at an intermediate stage to produce additional power. Casing or shaft arrangements. These arrangements include single casing, tandem compound and cross-compound turbines. Single casing units are the most basic style, where a single casing and shaft are coupled to a generator. Tandem compound are used where 2 or more casings are directly coupled together to drive a single generator. A cross-compound turbine arrangement features 2 or more shafts not in line driving 2 or more generators that often operate at different speeds. A cross-compound turbine is typically used for many large applications. Two-flow rotors. The moving steam imparts both a tangential and axial thrust on the turbine shaft, but the axial thrust in a simple turbine is unopposed. To maintain the correct rotor position and balancing, this force must be counteracted by an opposing force. Thrust bearings can be used for the shaft bearings. The rotor can use dummy pistons. It can be double-flowed. The steam enters in the middle of the shaft and exits at both ends, or a combination of any of these. In a double-flow rotor, the blades in each half face opposite ways, so that the axial forces negate each other but the tangential forces act together. This design of rotor is also called two-flow, double axial flow, or double exhaust. This arrangement is common in low-pressure casings of a compound turbine.